Hello there, and in this video we're going to continue our consideration of correlation and its interpretation. Let us assume we conduct a study on a beach and we measure the average temperature on any given day and record how many ice creams that a particular store sells on that particular day. And let us assume this data in this table is the observations of our data. So a couple things that we could claim in this case. So we could claim that as our temperature increases, the sales will increase. Now, is this true? Does temperature T actually have something to do with the sales, or is there other things going on here? Alright, so how can we sort of understand this type of scenario? So one thing we can do is calculate the covariance between the temperature and the sales. So if you do that, this is equal to covariance.s of our T set and our sales set, you're going to realize this is approximately equal to 14.67. So here, T is sometimes referred to, recall, as the explanatory or independent variable, and S is sometimes referred to as the response or dependent variable of the study. Alright, so we calculated our covariance. We can also calculate our standard deviations. Sx, for example, is going to be 2.98, and Sy is going to be equal to 4.79. So here I'm calling Tx and Sy to avoid confusion in notation. Alright, so once I calculate these, I can calculate my correlation coefficient, R. So remember, R is going to be the covariance of x and y divided by the product of our standard deviations. So in this case, that's going to be 14.67 over 2.98 and 4.79, which is approximately equal to 0.98895. And remember, you can calculate this in Excel using the function Pearson. So here you're going to do your x values and your y values. So keep that in mind. So from this number, we see that there is a positive correlation for sure. So once we have our R value, we can calculate our R squared value from this. So this is going to be equal to 0.98895, the quantity squared, which is about equal to 0.978. So maybe from this we can say that there's a strong positive correlation, and that is of course a subjective adjective here. Alright, so that's pretty much a basic breakdown of the covariance and correlation between these two variables. But there are some important questions that we need to ask ourselves here. So question, does T actually affect S and cause it to change? So in practice anyway, one usually can say not necessarily. It may be by chance. But if R squared is approximately equal to 1 and 0.978 could be subjectively reviewed to as close to 1, then that implies possible causation between x and y. So this high, strong correlation between x and y can imply possible causational effects between x and y, but not necessarily it implies that it actually causes one another to change. Another super important thing to keep in mind is other variables could be impacting the sales as well, i.e. other explanatory variables. So what do I mean by other explanatory variables? So we have our response variable y. So y is going to be the sales of ice cream. And we have our explanatory variables x, which we only considered temperature. But there could be other ones as well. So I can call this x1. X2 could be a holiday. For example, if there's a holiday, then the number of ice creams may be significantly higher than on just a normal weekday. X3 could be the prices. So probably as prices increase, the number of sales will decrease, possibly, who knows. X4, crowdedness of the beach. Some people may not like crowded beaches, so that will cause the sales of ice cream to decrease. Or crowdedness of the beach might imply popularity, so that may attract more people and cause the sales of ice cream to increase. Who knows? X5, advertisement, may also be contributing to the sales of ice cream, so more advertisement may bring in more customers, and so on. To this study. But usually, so far in this study, we've only considered like a y equals mx 1 plus b type of model. But technically, this is the most basic case because we're only considering one explanatory variable here. But in general, you may want to include other variables, say x1, x2, x3, x4, and x5 into your study, right? So usually one may call this, say, like beta 1, beta 2, beta 3 plus beta 4 plus beta 5 plus beta 0 here. So here's pretty much like a multi-linear regression. Model for that. But of course, if we use a multilinear model for this, that implies that there's a linear relationship between every one of the x values and y. But it could be quadratic or exponential or logarithmic or just totally nonlinear or not a simple transformation of a linear variable. But that's another discussion for another day. But this is just some things to think about when you start doing some correlation studies between variables. Namely, one, if there's a high correlation, it doesn't necessarily imply causation. And two, if there's no correlation whatsoever, there could be another variable that's sort of impacting your data study. So there might be a correlation, but one of these other variables like x2 or x3 is sort of clouding or causing some noise in your study. That needs to be considered. But we'll consider these multivariable cases at a later date. But that's pretty much a basic idea, run through of some basic correlation and causational discussion concepts.